of the shell. What is the meaning of equipotential surface? The name itself suggests what it is. Equipotential surface. A surface where the potential is the same all over is called an equipotential surface. Now tell me, is the surface of a charged sphere or a shell, is it an equipotential surface? Yes, we just said potential at any point on the surface of a charged shell or a charged sphere will be kq over r. Therefore, the surface of a sphere, a charged sphere, is an equipotential surface. A surface where the potential is the same all over is an equipotential surface. The electric field on the surface of a conductor, we talked about it. You have a charged conductor on the surface. The electric field always is at right angles. So the electric field on the surface of a conductor is perpendicular to it since there is no field on the surface. That means the surface of any charged conductor, you see, you take any charged conductor, irrespective of the shape, the surface of the charged conductor is an equipotential surface. Why? Because the electric field on the surface of a charged conductor is zero. I showed it to you in the last class. If the electric field is not perpendicular, if the electric field is like this, then there will be a component along the surface. And if there is a component of electric field along the surface, it will make electric charges move on the surface. And since it does not happen, we know there is no electrical field component along the surface. That means electric field is at right angles to any surface that is charged. Now, if the electric field is at right angles, there is no electric field along the surface. If E equal to 0, that means the potential is a constant. So, the conclusion is the surface of any charged conductor is an equipotential surface. The potential at any point on a charged conductor will be 0. Since E equal to 0 on the surface, V, the potential, must remain a constant. Very important. Now, you can see the surface is an equipotential surface. How about this surface that I have just drawn? Well, you can actually draw many surfaces as long as the electric field remain at right angles to the surface. You know that there is no electric field along that surface. Therefore, that surface also is an equipotential surface. You see that? If you have a surface that is at right angles to an electric field, it is an equipotential surface. All right. Irrespective of the shape of a conductor and the charge it carries, the surface of a charged conductor is an equipotential surface. Equipotential surfaces can also be constructed outside a conductor by drawing a surface that is at right angles to the electric field. Any surface that is at right angles to an electric field is an equipotential surface. The potential at any point on that surface will be the same. Let's now talk about distribution of electric charges on a conductor. Now, let's look at a couple of conductors. If I have a conductor like this, and if I charge this, how would you think the electric charges are distributed? Will there be regions where charges accumulate, and will there be regions where there will be very few charges? Or will the charges be uniformly distributed? Well, That is what we're going to talk about here. Distribution. How are the excess charges distributed? All right. Now consider a conductor of this shape. Well, it is kind of a pear shape. Doesn't matter. Some irregular shape. Now let's consider two regions of that conductor. This is region A and that is region B. If you look at A is, well, is part of a sphere of a certain radius. Tell me which of the regions, A or B, has bigger radius? A has larger radius. If you construct a sphere around the region A, the radius of that sphere will be greater than the radius of the sphere at B. Is that right? Okay. Now the radius of curvature of the surface is greater at A than at B. If R1 is the radius of curvature at A and R2 the radius of curvature at B, then you know R1, the radius of curvature at A, is much greater than the radius of curvature at B, that is R2. If sigma 1 is the surface charge density at A and sigma 2 is the surface charge density at B, then approximate expressions for potentials at A and B can be written as, you see, if sigma is the surface charge density and R is the radius, then you can write an approximate relation for the potential at a point on the surface as potential is sigma multiplied by the radius. Well, I'm going to leave it for you to figure out. It can be done and it is true. Now that means the potential at A is then sigma 1 R1. Potential at B will be sigma 2 R2. Well, tell me, what is the relation between potential at A and potential at B? Didn't we say just about 5 minutes ago that the surface of a charged conductor, irrespective of its shape, is an equipotential surface? That means the potential at A must be equal to the potential at B. Since the surface of the conductor is an equipotential surface, the potential at A must be equal to the potential at B, or sigma 1 R1 must be equal to sigma 2 R2. What does that mean? It means because R2 is much less than R1, for this relation to be good, the sigma 2 has to be greater than sigma 1. That means if the shape of a conductor is like this, the charge density is going to be greater where the radius is smaller. The charge density is less where the radius is bigger. So charge density is greater where the radius is small. This means that the surface charge density at sharp corners and pointed ends in the conductor is much greater than at other parts of the surface. For example, if I charge this conductor, look at this conductor. This has a sharp pointed end. That means if I charge this, most of the charges will be concentrated here where the radius of curvature is very small. So when an object is charged, there will be a concentration of charges at sharp pointed ends. Now, in the last lesson, I talked about you getting shocked when you touch your car. I'm sure most of you have experienced it. You see, if you are in the habit of getting shocked from your car, the best way to do that is go and grab the door handle with all your fingers. Don't just go and touch with one finger. You know why? When you are charged, the charges will be concentrated at the tip of your fingers. So if you go and touch with one finger, all that charges will try to jump across at that point, creating a very uncomfortable shock. Whereas if you go and grab, you increase the area, that means you reduce the shock. Now, this has got some very interesting applications. Now, let's talk